So some updates. Your exam is gonna open next week. And it's gonna be due, so your exam is gonna open next Friday morning on March 12th. And it's gonna close on Sunday evening at 11:59 p.m. See. Also, you guys have face-to-face. So you're gonna have face-to-face labs. Either you can make the April 9th or April 10th. So those are gonna be your face-to-face labs. I'll give you guys the times that you guys can come during that time period, blocks. We should be able to fit everybody in since you guys have such a small class. No issues.
I was going to ask if we were going to have to do a sign-up sheet again.
Well, for my benefit, we'll do it differently than we did it last time. I'll send you guys a doodle survey, and then that way we can get the times done. Then I'll send that out. I'll send the results.
Is the lab in Colina?
So there will be one in.
Is the lab in Colina?
There'll be one in Fireball as well for you. Gracias.
Okay.
Okay.
Yes.
And I don't have access to Lemoore for those who are in Lemoore, so you'd have to come to Kalinga. So, although I can see about that, I should for the future. So, are there any questions regarding that?
What chapter is this going to be on the exam? Just chapter 6?
No, it's actually going to be chapter 6, chapter 7, and a little bit of chapter 8. So that's why we're waiting till next week to actually open it up.
Okay, and then are we going to have a practice exam or no?
Of course.
Okay.
Yeah. Don't I always give you guys a practice exam?
Usually, yeah.
Yes.
I spoil you guys. Isn't that right, Jess?
Also, I got a question. How is the group projects going to work? Like it says right there in the grading part that March 6th is when we have to turn in a video explaining the project.
Yep. Okay, so the way the group project is going to work, you guys are in the evening section, right? So you guys need to get together at some point to start discussing which, and you guys got the email of all of the different papers.
Mm-hmm.
Yeah. So you guys got to decide which method that you guys are planning to use and how you're going to go about it. We also need to start ordering supplies for those items. The way it's going to work is we're going to set up a couple of times, kind of like an open lab for you guys to come in to test your products, but you're going to do a lot of the formulations by talking to each other and interacting with each other to kind of get you guys planned. So when you guys come into the lab, you have to have a lab plan, and that lab plan has to be approved by me at the end of the day. Okay? Do you guys understand what I'm saying?
Yeah.
Yeah.
So that just means we're just going to have to set up a Zoom meeting.
Yep. So you guys let me know when you want to set up your meeting, and I think you guys can do it. You guys all have access. I'll give you access to Zoom via Canvas, and so you guys can go in on Canvas and then click, and then you guys can set up a meeting yourselves. But I think it's like 30 minutes is the limitation on your time stuff. But if you want more time, then you could, you guys can actually set that up as well too. So via me. Or I believe Jess has power now too, right, Jess? Jessica, are you there?
Yes, Dr. Henry, I'm driving, but yes, I'm here.
Okay. Hey, you're starting to sound like me. Always on the road.
Yeah, I know.
Okay. Let's see what else. So it said face-to-face, April 9th or 10th. And then we have the first exam, the 14th. I know it's a little late, but it'll all be good in the long run. Okay. Questions, concerns, Pat? Okay. Okay, so let's go ahead and start with the lecture. And then you guys still have that simulation, the second simulation. On Wednesday, you guys will have another lab. You guys will be building, you need to start building your paper craft spectrometer. So get the instructions, get your black paper. Kayla, do you have black paper? Did I give you black paper and alligator clips and all those good things?
Me?
Yes.
I have to go check.
Okay. So you need your black card stock. You're gonna cut it out, cut out your little spectrometer, and then you also should have your slide that you're using as well. So you want to make sure that you have all of those items and put it together early, because then it makes it easier to do the lab rather than spending the lab putting it together. And then
Okay.
also have your cell phone ready. So you'll need glow sticks. You guys should have a total of 9 glow sticks. There should be one pack that's already open. There should be one pack, and that's the one you're going to use first. There should be one pack that has 3 different colors. That's going to be the second one you use. Okay. The third one you got to save for another lab. Okay. You should also have 7 LEDs. You guys, and then so your alligator clips, you should have your alligator clips connected to your LEDs. And you should also have $1 million for Dr. Henry.
I wish I had $1 million for myself.
Yeah, I thought I could squeeze that one in there.
Is there going to be like a paper, like a lab sheet to print out for the lab on Wednesday?
Yes, it's going to be actually, I'm going to finish it up tonight. I've already started it. It should be finished up tonight. So, and it'll give you the exact details of how to go about it. It'll be under the assignment, so you can actually print it out that way. So, yeah, because I had to modify a couple of labs and then also use another tool. So that I'm learning to use myself as we go. Pretty exciting. So, Mauricio, one day what? Well, the lab is going to be done on Wednesday, if that's what you're asking. So Wednesday. Yeah, and you should be able to get them all done in one day. It won't take you that long because all it is you're going to use you're going to turn off all the lights, be in the dark, and take pictures with your cell phone. Oh, one day, $1 million. Yeah, perfect. One day for $1 million. It works great. So if any of you guys win the lottery, you can just give me my $1 million and we'll all be happy, right? Okay, so let's get started.
I'm gonna be in debt.
Maybe we may get started. Okay, wrong class. This is what happens when you teach too many classes. You lose track of everything. Okay, so you guys are familiar with quantum numbers, right?
Mm-hmm.
Good. We've talked about the Z effect, right? The Z effective?
Yep.
Okay, good. Okay, so now you get to learn why all of that stuff is important. Okay, can you guys see my nice blue screen? Now it's no longer nice and blue. Are you with me?
Yes.
Good. Okay, so many of the properties of the elements are kind of dependent on our electronic structures, depending on what the number of electrons you have and what's going on in the case of the electrons. Okay. So the number of electrons are going to affect certain things, such as the size of the atom or the ion. It's going to affect ionization energy. It's also going to affect the electron effect. Okay, so we're going to kind of talk about that and talk to you about how these electrons play a part in this, as well as the result of it. And so we're going to pay attention to a lot of the trends that are going on in the periodic table. So one of the first things that is affected by is the covalent radius. So the covalent radius is basically the radius of two atoms that are bonded together covalently. And so it's two atoms who are bonded together covalently, and it's the distance, half the distance between the two nuclei of those atoms. So that's going to be your covalent radius. So, and I'll show you an image of that right now. So here's an example of like fluorine. So we have fluorine bonded together, chlorine bonded together, bromine bonded together, and iodine bonded together. So the radius, the covalent radius, is just the distance from nuclei to nuclei and just half of them. Okay. So there's a trend that as we go down the groups, and it makes sense because that means you're adding shells of electrons as you go down, right? So it's kind of like, have any of you guys seen the Russian dolls, the little Russian dolls that fit inside of each other?
Yeah,
Yeah.
the nesting dolls.
Oh yeah.
Yes. Okay, so it's just like the Russian dolls, right? So the first period represents that small little doll. The second period represents the next one, the third period. And so it's just adding on. So as you go down groups, right? So meaning you're going through those periods, you're going to get bigger, right? So the atomic size is going to increase as we go down the groups, okay? And then because of the effective nuclear charge, Z effect, right? So basically that is just telling us that it's telling us the pull or the strength of the nucleus, right? So the Z effect basically tells us if the nucleus is bigger. So if the Z effect is actually going to increase from left to right, because you have more positive charge in the nucleus than you have, say, the electrons, right, that are shielding it. And so as a result of that, the size of the radius is going to get smaller because your nucleus is really strong, but it's pulling all those electrons closer to it because it's stronger. So as we go from left to right, the size of the radius is going to get smaller, okay? But the Z effect is going to get larger. You see how that works? And does that make sense? So if we look at the periodic table, second, there we go. As we look at the periodic table, as we go from left to right, the radii getting smaller. As we go from top to bottom, the radii are getting larger. Okay, so knowing that, who's going to have the fattest butt on the periodic table?
The ones towards the bottom.
Okay, so what particular element?
FR.
FR, that is correct. So francium would have the biggest butt because it's going to be the largest point here, and it's going to be even larger at the very bottom. Okay, so on period 2, which element is going to be the smallest?
Beryllium.
Beryllium,
The smallest.
the smallest.
Neon.
That's right, neon, right? Because as we go across from left to right, it's going to get smaller. But you're bringing up an interesting point because we know that there are going to be some exceptions. There are exceptions. Regardless of what I say, there's always going to be a couple of exceptions. So we know the general trend, but there's always going to be 1 or 2 exceptions that break that rule. Okay, and you can kind of see that here in slides. Oops. Okay, so, and as you said, you're basing it on what you saw. So beryllium is actually pretty tiny, and so that's one of your exceptions. Okay. Questions, concerns, Cash? Okay, so this is just basically showing you that trend. So here you have helium that is pretty small, then you go back up to lithium, and then it just goes down to neon, and then so on and so forth. So the ones in that first period are typically largest. The ones that are typically smallest are your noble gases. Questions? Good, no questions. Makes it easy. Okay, so when we're talking about ions, because in the case of ions, we have to take in consideration our Z effect, right? So do you guys remember how to calculate the Z effect or Z effective? Yeah, no, maybe?
Isn't it
Yeah.
like the total number of electrons minus all of the non-valence electrons?
Okay,
Well, I mean, not total number of electrons, but the atomic number.
the atomic number, that's right. Atomic number minus the non, yes, essentially. Okay, so then that allows us to sit there and calculate the Z effect. Now, again, if you think about it logically, so if you've lost an electron, let's say you have Na plus, right? Na plus means that you've lost 1 electron. So if we compare Na plus to neon, which one will we expect to be smaller? Na plus or neon? Are you sure?
Neon.
Are you sure? Okay, let me ask you this. We'll do neon and, I mean, not neon, sodium and sodium ion. Which one would we expect to be smaller?
Ion.
The ion is going to be smaller. Why?
Because the plus actually is taking away an electron.
Yes, because the plus is all in the middle, right? So it's going to be pulling those electrons closer to it, right? So my next question, sodium has how many How many plus charges does sodium have compared to neon? How many protons does sodium have compared to neon? Anyone? Anyone?
11.
11. And neon has how many?
10.
10. Okay. Sodium plus has how many electrons?
10.
And neon has how many electrons?
10.
Okay. So which one would we expect to be smaller now that we see this? Then we'll do this guy, 11 and 11 electrons. Anyone?
The
Would
sodium?
neon be the
Yes.
smaller?
Which one?
My guess is neon. I'm not sure.
Your guess is neon.
Are they the same? Do they have to be small?
One would be smaller than the other. And
Oh.
why? Why would you think it would be smaller than the other? So this is the number of protons. Where are protons
Oh.
located?
Oh, is it because like the electrons aren't as like heavy?
The electrons aren't as heavy, so but that isn't the reason why. What's happening in the case of the protons? Protons are what?
The protons are in the nucleus.
They're in the nucleus, and what type of charge are they?
Wait, what was the question?
What type of charge are they? Protons.
Oh, positive charges.
Positive, right? So they're in the center of the atom, and your electrons are negatively charged. So what's going to happen between those negative and those positive charges? What's keeping those electrons in orbit?
They're attracted.
They're attracted, right? So who's going to be more attracted? Meaning that who's going to compress more? The one that has 11 protons in the middle, or the one that has 10 protons?
The one has 11. So would Na
One that-
plus be the smallest?
So sodium plus would be the smallest. Yes, because it's going to pull those electrons tighter to it because it has more positive charge in the center. Does that make sense?
Mhm.
Okay. So let's say we have and let's do, okay. So which one of these will be, let's just look at the nitrogens. Which one will we expect to be the largest out of the nitrogen? Nitrogen 3 ion, nitrogen 2 ion, or just nitrogen? Which one will we expect to be the largest?
3 ion?
The 3 would be largest. Then who would be the second largest?
2.
And then nitrogen, right? And then that makes sense because in that case, you're adding an electron on the outer shell, so it's going to be bigger, right? So your pull on the inside isn't going to change. So if we compare the largest here to neon, who's going to be bigger? Neon or the nitrogen ion, nitrogen N3 minus ion?
Which one's going to be the largest?
Which one is going to be bigger? Yes, it's going to be bigger.
The neon?
Are you sure? Okay, so let's think about it. How many electrons does N3 have?
10.
10 electrons. How many protons?
7.
Okay, neon, how many electrons does it have?
10.
And how many protons?
10.
Okay, so which one's going to have the stronger pull? They have the same number of electrons. Who's going to have a stronger pull in the middle? The 7 protons or the 10 protons?
Cross.
Anyone? Mauricio, my go-to.
Yes.
So who's going to have the bigger
Mary.
pull in the middle? 10 or 7?
It's gonna be. Well,
You said it's going to be 10.
nitrogen ion gonna be bigger. Yeah.
So the nitrogen ion is going to be bigger. So the neon ion is going to be smaller. Right? Simple?
Yeah.
Yeah? No? Maybe?
Yes, it's simple.
Okay. So this here just basically shows you exactly what we just talked about. So we have the aluminum ion and we have the aluminum. And so you can see that aluminum ion is significantly smaller than the aluminum. And then we have the sulfur atom and then the sulfide ion. Sulfide ion is significantly bigger than a sulfur atom, right? So as cations are going to be smaller than their atomic counterpart, and the anions are going to be larger than their atomic counterpart. Okay, make sense? Yes, no, maybe.
Yes, that makes sense.
I have a question, Dr. Henry.
Do you have any
So,
answer?
so you know how like in 2A and then in 1A, I believe, we learned how the trend on the periodic table.
Yep.
For these specific ones, it's just better to base it off like the protons, electrons, right? Instead of that trend because it changes because of the ions. Does that make sense?
You're talking about when we're talking about the ions relative to their atomic counters?
Yeah.
Well, you want to do both. You want to base it off of both, right? You want to base it a little bit off the trend, and you also want to base it off of the, off the ions. And so it's going to be a combination of both, right? So for instance, you know, the ions, I mean, you're talking about the electrons, protons, electrons. So now that you know the Z effect, you should be able to sit there and use the Z effect to sit there and give you an idea of that. But you can sit there and look, how many protons does it have? How many electrons does it have? And then how does that compare, right?
Okay, right.
Does that make sense?
Yeah, that makes sense.
Yeah. So, but you can use the general trend to kind of get an idea, but you definitely want to look at it at the atomic level or the subatomic level.
Okay.
Now that you know about it, right? Compared to what you knew in 2A, right?
Right.
Okay. Okay, so I got carried away. So ionization energy. Oh, before we get started, so this brings up the topic of isoelectronic. Isoelectronic means what? Isothermic, isotonic, I don't know, something iso. What does iso mean? Anybody?
The same.
The same.
I was thinking in isotopes.
Yep. Well, yeah, because it's the same atom, but just different weights, right? With the isotope. So isoelectronic basically means it has the same number of electrons, or the same electron configuration. So we know that N3- has the same electron configuration as neon. Oxygen has the same electron configuration as neon. F- has the same electron configuration as neon. So we know this because we know how to do electron configuration, and we know that it's going to be this. So they're the same number of electrons. Okay, so in that case, here's a question for you. Are they the same size? Even though they have the same number of electrons. Okay, Jess, there's a big pause here. Nobody's saying anything. So we're definitely putting this question on the test. Put in my notes right now.
I'm not sure if something is wrong, but the only thing I can hear right now is like,
Because it's called crickets. So what do you guys think? I mean, you got a 50-50 chance, right? So yeah, it is, or no, it isn't, or what?
No.
No.
No, right? So no,
Okay,
they're not going to
everybody.
be the same. They're not going to be the same size because it's going to be dependent on the number of protons in that case. And don't these guys have different number of protons?
Yeah.
7, 8, 9, 10. So which one will we expect to be bigger and which one will we expect to be smaller? All right, we've already done this exercise because we did nitrogen and neon. We do expect neon to be smaller because it has a larger Z effect. Okay. Simple. Good. Okay, so ionization energy. So ionization energy, the first ionization energy or ionization energy in general is the energy that is required to basically remove an electron from the gaseous atomic or the gaseous atom. So your first ionization energy is the energy to remove your very first electron from that atom. Your second ionization energy is the energy that's required to move the second electron from that atom. Usually, the ionization energy, it takes less to do it from that first one than it takes to do it from that second one or the third one. Okay? The third ionization energy would be the energy that's required to move the third electron from an atom. Okay? And so on and so forth. So you guys understand what it is? You want to hear the trends? So, so the trends are, as we go down the group, we're going to get a decrease in ionization energy. So it's going to be easier to pull electrons from like francium, right? Because francium is so big, it has such a big butt that it doesn't recognize when the electron is pulled from it, right? Where if we're back at lithium, lithium is going to recognize it. It's going to take a lot more energy to remove it from lithium than it would to remove it from francium. That's where they're located at. Okay, that makes sense? And also the ionization energy is going to increase as we go across, right? So in the case of neon, right? Or helium. Helium is going to have a really high ionization energy. it's going to take a lot of energy to sit there and remove that electron from helium. Why do you think it's going to be so? It's going to take so much energy to remove an electron from helium. Anybody want to take a guess?
The electron is very close to the nucleus.
The electron is very close to the nucleus, right? Since it's smaller and it's more compact, and it's keeping everything really tight. And then helium is also a noble gas. If it gets rid of an electron, will it be a noble gas?
No.
No, it wouldn't be a noble gas. It's going to be far from it, right? So then it's going to be more like hydrogen. So it's not going to want to give up that electron. It wants to, because it's stable now. Would you want to be unstable? So if you have everything going for you, your life is going for you, everything's really going really great, are you going to all of a sudden say, well, you know what? I'm going to start practice. You know, I'm happy in marriage. I'm happy. I just want to start practice. I want to screw up my life. Do you guys do that? Right? You said you're on the verge of doing that? Please don't. Okay, so stability, right? So it's already stable, so it wants to stay that way. So it's not going to make those changes. Okay, make sense? Okay.
Yes.
So this is just showing you the trends, right? So helium has the highest, then neon, then argon. So you'll notice how the trend set. So here's hydrogen, helium's greater than hydrogen. And we go from lithium, beryllium, boron. And so you'll see these really rare exceptions, right? So we went from beryllium to boron. Boron is lower than beryllium, and then we go back up. Now, this is also because we have, take a look at beryllium. Beryllium has its 2s shell, Bill, right? So we have things that are going in both in opposite directions already. So it has a low energy state already, right? So it's kind of like, you know, I'm pretty cool with it like this. Where boron has this lone electron in the 2p shell. So it's like, you know, hey, I'm cool with it. I don't take as much energy. I mean, it takes energy to do it, but it doesn't take as much energy as it would take for beryllium, which is here, a little more stable. Does that make sense? I guess not, or I guess so. So I'll just take it as so because nobody stopped me. So this is just basically showing you the numbers, the values, and you can also find this on P table. So if you go to P table, and then you scroll up, ionization energy, right? So this is the ionization energy. This is your first ionization energy. This is the second ionization energy. This is the third ionization energy. Okay, but you'll notice, let's say our first compared to our second. So it takes more to get that second electron out than it takes the first. Okay, questions, concerns, Dash?
Weather, checks, credit.
Can you do another example of what you did?
Can you repeat that? Yes.
Can you do?
I'm going to mute you for a second. Okay, now go ahead.
Okay. Can you do another example like you did previously, the 2s, 2p? Like
Yep.
another element, please.
Sure. Okay, so let's say we have magnesium, right? So magnesium here, this is the 3s. Of course, we have the 2p. And we have the 2s. And so we're not going to worry about, all right, I'll just put the 1s just for hell of it. Okay, so here we have magnesium. Okay, So if we compare magnesium to, let's say, let's do aluminum. Aluminum is be the same for all of the ones down here. So I'm going to erase this here. I'm going to borrow this. Maybe. So 1s, 2s, 2p, 3s, 3p. Let me close my door. Okay. So, oops. Okay, so you guys remember the whole concept of Hahn rule and the Pauli principle and all of that stuff, right?
Yeah.
Mauricio says no. Okay, so Hahn rule basically, do you guys remember what the Hahn rule says? Hahn rule says what? What is the maximum you could have in an orbit? In each orbital, how many
The
can you have in it?
maximum?
Maximum, yeah. How many? This is an orbital, this is an orbital, this is an orbital, this is an orbital. What is the maximum I can have?
2.
2. Okay, so then we also have what we call like the Pauli exclusion principle. I'm mixed up. Where we have to fill up individual shells first, right? You guys remember that? Where we first have to go through, well, the S fills up before we fills up the P. Then when we get to the P, we do this first one, put one that way, and then we put one this way and one this way. You remember that?
Kinda.
Okay, so as we're putting in our electrons, we put them in this way, all facing the same direction first, one in each orbital, and then we come back, and then we put them in the other direction, right?
Yeah.
Okay, good. Okay, because these guys here are all the same energy level, which is higher than the 3s. This 3s guy, if it was just at the 3s, this guy is more stable than this guy because it has this lone electron here. So this guy is going to be anxious to get rid of this lone electron. So its ionization energy is going to be lower because ionization energy is the ability to get rid of an electron. Its ionization is going to be lower than this guy because this guy is more stable because it has an electron going in one direction and it has a counterpart going in the other direction. Otherwise, you only have one going in one spin in that orbital, like this guy does up here. Does that make sense?
So it takes more energy to take it from the S orbital, or
That's right. It'll take more energy to take it when the S orbital is full. If the S orbital was just, if it had just one, like in the case of sodium, let's say this is instead of magnesium is now sodium, then it's going to be easier to take from sodium than it would to take from magnesium.
so
Right.
why is the S group energies a lot lower than the P group?
Because that's it. It's the energy. So if we look at the ionization energy, it's the energy that is needed to remove an electron. So the S is lower than most of the P, right? So we see this is the one, this would be the first electron here, right? So If we remove this one, it's less energy to remove that electron than it is to remove this one in magnesium. Does that make sense? So this is magnesium now.
Does it have to do with the analogy you would give? Like, it's easier to steal a kid that's far away from its mom than a kid that's closer?
Yes, it has to do with that. And also, if the kids are in pairs, right? If they're with a friend, it's a lot harder to steal two kids than just, or to steal one of those kids if there's another kid there, right?
Ah, okay.
Okay. So in this case, since it has a pair, it's harder to take away from it. So that's why the ionization energy is higher, right? So, and if you look, it goes sodium is low in ionization energy. Then you have manganese. But then if you go to aluminum, aluminum has that one lone in that upper energy level. So it's going to be easier to pull away from that aluminum compared to magnesium, because this guy is paired in the s orbital. Does that make sense?
Oh, okay. Wow, that's me and my cousin trying to get away from our parents.
Yes, yes. Okay.
But what about like the other ones, like oxygen? How it's like 1300?
Yeah.
Or like,
Because here in the case of nitrogen, right? So if we look at nitrogen in the, that would be the 2p. So we'll use this upper one to say it's nitrogen. So in that case, nitrogen is like this, right? Which is more stable than, let's say, the oxygen, which has that one. Now we're going to say these guys down here are oxygen. And then this guy is oxygen. So you have this going on. Okay. So you have that lone one that's going down. And so that screws things up, right? And then you have these two that are, you know, at first they're kind of counteracting different shells because each of these are in different orbitals, but they're spinning in different, like one is in the z-axis, one is in the x-axis, and one is in the y-axis. So it's giving it a little more uniformity compared to having these guys that are kind of balancing each other out. And these guys no longer have that uniformity because they don't have that pull, that same type of pull in the x-axis that they would have in the case of these, where it's the y and the z. Does that make sense?
yeah.
Okay. So like, you guys, have you played with widget spinners, right? And then you're just spinning. It has 3 points with a 3-point widget spinner. Now they're all even on all three sides, right? Same distance. If we decided that we're going to shift it over a little bit, is it going to stay on our finger or is it going to fly off our finger if we don't use the center exactly?
Oh, it'll like fall to one side.
Okay, so it'll fall to one side. So that's kind of like what's happening here. So you have these two electrons here, right? So at first we have something here, we have something here, and we have something here, right? So all of these guys are equal distance apart. So let's say this is our nice little widget. So now what we've done, we've shifted over, we shifted this hole over, and now it's right here. So is it going to stay balanced? Now, since we have something that's a little heavier here than it would be everywhere else.
No,
No, right?
it's not.
So, and that's sort of what's happening in the case of oxygen. So that's why you see that dip between, let's say, nitrogen, then it drops down for oxygen, and then it goes back up for fluorine, which is a whole nother set of reasons. So, well, it was not a whole nother set, but it's just a little additive part of it. Okay.
Okay.
Does that make sense?
Yeah.
Okay.
Yes.
Okay. Okay, so we've talked about the beryllium already. And then, and we also kind of talked about that in terms of the effect it has. And then this is also talking about the oxygen, so our deviation, right? So sort of makes sense to you guys? Okay, and so once you remove that electron, it becomes more difficult to remove the next electron than when it was neutrally charged. So each time that you remove an electron, it gets a little bit harder. Okay, and this is just basically showing that. So here's potassium. So this is removing that first electron. Then after you remove that first electron, you try to remove another one, it gets really, really hard. Then it gets harder and harder each and every time you try to remove an electron. Okay, you see that trend?
Okay.
Everybody gets it? Piece of cake?
Yeah.
Okay, so okay, so electron affinity. Electron affinity basically is the desire, the energy that it's going to take to add an electron, right? So this process could either be endothermic or exothermic, right? So if it's going to be, if it has a negative electron affinity, that means it's going to be releasing energy. So if it's releasing energy, it's exothermic, right? So if your value is a negative value for your electron affinity, then that means energy is being released from the system. If your value is a positive value, then that means you have to put energy into the system to make it happen. Okay. Okay, so the trend is for electron affinity, it becomes, as we go across periods from left to right, then it becomes more negative. There are going to be deviations in here too, or people that break the rules all the time. Okay, so
Ooh, that's me.
you're a rule breaker.
Yes,
Okay.
I've been like.
And some of these rule breakers are going to be consistent. So we know that the noble gases, right? So the noble gases have a completely filled energy shell, right? So in that case, it's going to be a lot more work to add an electron to that because it's already happy. Does that make sense?
Yeah.
Okay. So, and then group 2, because the group 2, the S subshell is filled, and so it's going to take a lot more energy again to sit there and try to push that up again. And then group 15, because it's half full, same problem. So when we take a look at this, okay, so we have group 2. So this means that no energy is required. You know, it's going to happen. So it can happen. It's not favorable because this is a very low negative number, right? So this guy means that we have to add energy to it to make it happen, right? A lot of energy. So it's not happy to do it. And so you see the same trend here for group 15. You get down to 0 compared to the others. And then the noble gases, right? So these guys, it takes energy for all of them to put in there except for neon, where it has a very small release, but it's a very small relative to the others, right? So this guy is anxious to get that electron, so it'll release. It's happy to do it, right? Since the negative value. So does that make sense? Yes, no, maybe.
Kinda.
Okay. So
Maybe.
if it's positive, you have to put energy in it, right, to make it happen, right? anytime you're putting energy in, you're trying to force it to happen, right? How many of you guys, let's see, how many of you guys gamble? Anybody gamble? Go to the casino, hit the slots.
I've gone like maybe once or twice, but I always lose money, so.
Okay, me too.
Oh no, I'm still underage.
You're still underage? Okay, so maybe that gambling is not a good analogy. But so if you guys go to the casino, like right now especially, so the casinos are looking to try to make some cash. You know, COVID, their numbers are not as high as it normally is. So they're just trying to make cash left and right. So your odds of winning are probably a lot less than what they would be had COVID not happened, right? Because of that, people have a tendency of chasing wins. So they put more and more and more money into it rather than getting money out, right? So here you have to put, to get a win, you're trying to force to win. So you're putting a lot more money in, right, to make this happen. Where here, you're getting money out, okay? So that means it's releasing money, right? So that's a good thing for us. So this is gonna happen without putting anything in. This one is gonna require us to put some more energy to make it happen. Okay, so for us to get an electron, for this guy to take on another electron, you have to put a crap load of energy. Where fluorine, right, it's just like, oh, it's gonna happen, right? Fluorine's like, yeah, give me that electron. I'm not gonna fight you for it. Give it here right now, you know? Where beryllium is gonna be, no, no, I don't want it. No, 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 okay? Simple?
Yeah, that makes sense.
Okay. So let's see how we're doing on time. We're doing pretty good. Okay, let me pull up my other lecture. 7. Okay. We're gonna whip through this one as much as we can. What's wrong one? Wrong lecture. Oh, right lecture. Okay, so chapter 7, we're going to be talking about ionic bonds, covalent bonds, Lewis dot structures, and structures in general, formal charges, resonance structures, strength of ionic and covalent bonds, and we're going to be talking about molecular structures and polarity. Okay, so you guys remember, we've gone over this. This should be like in the back of your head. So ionic compounds. Ionic compounds consist of 2 ions coming together based upon their ionic charges. Okay, so like for instance, we have sodium metal and we have chlorine gas. So sodium metal wants to do what? Now, you guys remember, let me go back. Maybe I'm getting ahead of myself.
Gain an electron.
Does it want to gain electrons or does it want to lose electrons? Anyone? Here's sodium.
Lose one?
It wants to lose electrons. Okay, so just a reminder. Now, I'm going to ask you this. Mauricio, are you there? Yes, no, or did we lose him? No, we didn't lose you. You're here still?
Yes, I'm here.
Okay, good. Okay, so we'll pose this question to you, Mauricio. So, Mauricio, now, when you guys were, well, we'll say everyone. When you guys were in high school, were there cool kids? Did you guys have cool kids at your school that everybody wanted to be like?
I mean, not really, to be honest.
Not really? Okay,
No,
so that
because
term,
only in junior high it's when they act all cool.
okay, it was only in junior high? Okay,
Yeah.
so what about the term nobility? What does that mean to you? Nobility, noble.
Well, if it's about high school, it wouldn't be like the kids to have, well, that are more smart, let's say.
Okay. Is that what it means to you, to be smart?
Also to have more resources as well.
Do any of you guys watch, what is that show? Game of Thrones, or watched Game of Thrones when it was popular?
Oh yeah.
I hated the season finale, or the series finale. I should say season finale. It was horrible. But did you guys watch Game of Thrones?
Yeah.
So they talked a lot about nobles, you know. So what was their definition of nobles in shows like that deals with like fantasies, knights and kings and all of those things? Anyone? Alberto, what does noble mean to you?
I think it's like respectable, or like, for example, with people like someone you look up to or trying to be like.
Somebody you look up to or trying to be like, right?
Yeah.
So why do people, what was that?
Also wouldn't be someone who is educated.
Educated, okay.
Mm-hmm.
Okay. So respectable, educated,
High class.
somebody high class. Okay.
Wealthy?
Wealthy. Okay. So when I think about noble, I think about wealthy, right? That's what I think about. Or I think about stability, right? So they're stable. So I guess educated could fall in that category of stability, right? So the noble gases, they're called noble gases because they're stable, right? So basically they have their octet, their outer shell filled, right? So they're not wanting to react. They're cool. They're like, oh, I'm good to go, right? So because they're good to go, they're not gonna want to sit there and react. But all of the other elements, such as carbon, nitrogen, all those guys, they're not. They want to react. They want things to happen so that they can be like the noble gases. So the noble gases are kind of like the Johnsons that everybody wants to be like, because the Johnson has, you know, they got the brand new Porsche, they got the Escalade, they have a beautiful house, they're all, you know, perfectly made up and everything like that, right? They're stable, you know? So the reason why things come together or they react with each other is so that they can become stable. And so the goal is to try to have some stability, right? So that's the reason why we have reactions, right? So to be stable, there's a couple of ways that you can do it, right? So one way is to give electrons away, so you can be like a noble gas, or you can take electrons, so you can be like a noble gas, or you can share electrons, so you can be like a noble gas, okay? And so that's the reason why you're gonna have these reactions, right? So when you have a metal and a non-metal, one is gonna be, the non-metal is gonna wanna take the electrons because it's over here, it needs one, let's say we're talking about nitrogen. Nitrogen will need 3 electrons to be like neon, 1, 2, 3. And it wants to be like neon. So it's gonna wanna get 3 electrons. Where this metal, let's say lithium, wants to get rid of electrons, right? So each of the lithiums are gonna wanna get rid of 1 electron so it can be like helium. Does that make sense? Yes, no, maybe?
Yes. I got
Okay.
part of them.
Okay, so the reason why we have bonds occurring or reactions occurring is because these guys want to become stable, right? How many of you guys say, okay, so my question to Mauricio. Mauricio, if I was like really, really wealthy, I had this huge mansion and all of this land, right? And I had like 50 million cars. And I come to you and I say, Mauricio, your eyes are just incredible, right? Your smile just, it makes me glow inside. Will you marry me? You don't have to have sex with me. You don't even have to live with me. But I just want you to be mine. What would you say?
What a toxic relationship.
You said, what a toxic relationship.
So you want him to be your trophy wife, Dr. Henry?
Yes, Mauricio will be my trophy wife.
I'm gonna have to say.
You're
Say,
gonna say
I
no.
do.
Oh, come on, please. You know, as soon as I come up with that, come up with my limo and everything like that, and I show you around, you'd be like, hell yeah, let me sign on right now, right? At least I'll tell you, that's what I would do. Somebody tells me that, I don't have to sleep with them. I don't have to do, okay, this works great for me. This is a perfect relationship. Let's go, right?
Let's get cash.
Yeah. So the thing is stability, right? So the concept of stability, the reason why we get into relationships is stability. Do you not get in a relationship to try to be stable? Or do you sit there and say, you're a crackhead. I want to marry a crackhead. I've always wanted to marry a crackhead because I love drama. Do you guys say that? Yes, no, maybe?
No.
No. So nobody plans to marry a crackhead. It happens by accident, right? You always are trying to look for stability, right? You're like, oh, I want love, I want this, I want that. But at the end of the day, you want stability, right? You want to be able to have something to share with somebody, to make money, to have kids, to have a family, to be able to provide for them, right? That's the reason why you guys are all going to school. Is that correct? So that's the same thing with these atoms, right? They want stability. So they're trying to find their way to stability. So that's the reason why they're going to interact. Okay, so as we were saying, lithium wants to be like helium, right? So it's going to lose one electron. So if it loses one electron, what is going to be the charge? You guys should know this already because we've talked about it millions.
+1.
+1. And then nitrogen wants to gain 3 electrons to be like neon, but it's going to be its charge.
-3.
-3. So if we put these together, because how many of you guys remember opposites attracts, right? How many of you guys did in high school? Everybody?
Me, of course.
Okay. Is Graciela the only person dating in high school? None of you guys dating in high school?
I was a baby still when I started dating.
Okay. So how many of you guys are dating now?
I'm at that point.
Yeah.
You're at that point?
Yes.
Yes.
Okay. But you didn't date in high school?
No, I
Yes.
wasn't.
Yes. Only Mauricio and me.
Okay. So usually when you date in high school, you can relate to this a little bit better than when you're dating now, but it may work for you now too. So have you ever you came home to your family and you're like, oh my God, I have met the most beautiful girl in the world. Man, she is gorgeous. Oh my gosh, I asked her out and she said yes. And you tell your mom who it was? Yeah, Chante Williams. Hey, Chante Williams, oh my God, I was so in love with her. And she said, yes, we're dating and everything like that. And your mom says, who? Chante Williams from the Williams family up the road? No, that girl is bad. She's been arrested 17 times, She's sitting there, she sells dope, And so your mom's like, no, you're not dating her. You're going to break up right now, right? I don't want to hear it. There's no arguing. You get your butt over there. You're going to break up right now. Call her up right now. Break up, right? Did that happen to you guys? Huh?
Yeah. When I was
Yeah.
13, I was dating an 8-year-old. My mom got mad.
Uh-huh. And then so what did you do, right? Did you go break up with him immediately?
I kept going
Uh-huh, right? Why?
because I liked him.
Because he was a bad boy. Opposites
He was
attract,
cute.
right? You're the good girl,
Yeah.
he's the bad boy. So you're like, those opposites are always gonna attract, right?
Oh yeah,
So that's the same thing
temptation
that's
is
gonna
always
happen
good.
here, right? these opposites are going to attract. So you have your positive charge and your negative charge, they're going to come together and they're going to form an ionic bond. Okay, so this ionic bond is going to be Ni3, I'm sorry, not Li3N, right? Or lithium nitride, right? So they're going to come together by electrostatic forces. Those opposite forces, they're going to come together and they're going to stay together. It's going to be pretty strong, right? Until water breaks them up. Okay. So long as it's a solid, this is a strong bond. It's a very strong bond, right? So if we heat it up, its melting temperature is pretty high, right? It takes a lot of energy to sit there and melt it. We're talking about like 600 plus degrees Celsius, right? Let's see, come on. Okay, so we have ionic bonds. Ionic bonds are basically composed of your ions. You guys know what ions are. They're also going to be called salts. Often we will use the salts as a very generic term. In this case, this is called salt specifically, right? Sodium chloride. So if we have the sodium metal and chlorine gas, sodium metal is going to want to get rid of an electron. And chlorine gas is going to want to gain those 2 electrons so it can make the chloride ion. So balance these guys out. We can add these 2 equations by, you guys remember that, we'll find this guy by 2. The electrons are going to cancel out. They're just going to be transferred to each other. So then you're going to end up with Na plus Cl2, sorry, 2Na yields NaCl. So these guys are going to come together because they're opposite and balance each other out perfectly. And the goal of ionic compound is to have a total neutral charge of 0 when they're coming together. Okay, so this ionic interactions, it prevents these ions from moving freely in the solid. So they're going to be stuck together based upon the charges. Okay, so they're going to form lattices. We'll talk about that here in a second. Okay, so here is an example of that lattice, right? So this is a crystal lattice of that sodium chloride. So you have a sodium. You have a sodium, you have a chloride, you have a sodium, you have a chloride, you have a sodium. And so they're going to be alternating based upon charge, and those charges keep them fixed. So this structure is going to be rigid, right? It's going to have very high melting temperatures and boiling temperatures. It's going to conduct electricity very, very poorly. Horrible at conducting electricity, right? Because they're connected, they're interacting. So those charges aren't going to be free to do anything. Okay. And again, this is going to be a strong bond. Okay, so this represents the energy that's associated with that bond. Questions? Concerns? Cash? Good. Okay, so here it's going to be a combination of ionization energy and electron affinity that determines whether or not you're going to want to lose an electron or whether you're going to want to gain an electron. Okay, so in this case, these guys, the ionization energy are relatively low compared to these guys. So these guys are going to want to lose their electron, right? Where these guys are going to want to gain an electron. Okay. So for metals or metallic elements, electrons are going to be lost easily, right? Where nonmetals, they're not going to want to lose electrons. They're going to want to gain electrons. So they're going to take those electrons that those metals are losing, Okay. So that's that concept of give and take. So I like to do the comparison, right? So if you have your neighbor, right? Let me, hold on. So these guys are your nonmetals, right? So your nonmetals. So your nonmetals are kind of like neighbors to each other. So if you have your neighbor right next door to you and they have this kick-ass motorcycle, and you're like, you're really eyeing it. That's a really nice motorcycle. So are you going to be likely to share that motorcycle with your neighbor or steal that motorcycle? You say, hey, dude, do you mind if I borrow your bike every once in a while, man?
I would.
You'd borrow it?
I would
Or would you-
borrow it.
Or would you steal it? Now, from your neighbor, now think logically. Now, think about it. Think about the consequence.
If he doesn't know me, of course, mine.
Okay, you would do that, right? He's your neighbor.
Yeah.
And so when you're riding down the street, what's going to happen? He sees you on his
He's
bike.
gonna chase me for the motorcycle.
Or he's going to call a popo on you, right? He's going to call the cops on you. You're going to go to jail, right? So
Yeah.
what is the likeliness of you stealing from your neighbor? Does it make sense? I know you guys are all smart, right? Does it make sense to steal from your neighbor?
No.
No, it makes no sense to steal from your neighbor, right? So, but if you saw the same bike with the guy that's 3 towns over, would you steal from him?
Yeah, I will steal from Mauricio. He doesn't know me.
Mauricio? Okay. So Mauricio, you better keep your bike locked up. You know where it's, you know, if it's missing, you know who to ask, right?
I know how to
So-
hack the passwords.
And that's essentially what's happening here, right? So these guys are like neighbors to each other. They're not going to steal from each other. So they're going to share, right? But a non-metal and a metal, right? So a non-metal will take from the metal, okay? Because one thing, it's easier to do that. It's less energy, okay? Make sense?
Yes.
Okay, good. But don't be stealing anyway, so. But if you do, don't steal from your neighbor, definitely, okay? At the end of the day, the charges has to be neutral, so they have to balance each other out, okay? And again, we've talked about this. We talked about it when we did nomenclature and stuff like that. This should all be just refreshers, right? Okay, so being it that these are refreshers, I'm going to put you guys into 2 groups, and then I want you guys to sit there and tell me the ion, each of the ions and their charges, and also tell me the compound chemical formula. Okay, and I'll give you guys, we'll say 5 minutes, 6 minutes.
So you want the ions and charges
Yep.
and
And then
formula?
And then chemical formula. Okay, I'll see you guys in 6 minutes. Okay, let's see what you guys know. Let's see. Sharing again. Or am I still sharing? I just had everything up. Okay. Oops, wrong thing. Skip. Okay. So what did you guys get? What was the chemical compound for lithium oxide? What does it look like?
Li2. O.
Magnesium nitrate,
Mg3 and 2.
aluminum sulfide,
Al2S3.
boron chloride,
BCl3.
calcium phosphide,
Ca3P2. I don't know why I'm laughing.
I don't know why you're laughing either.
I think I'm hyper.
Okay. Come on. Okay. Covalent bonding. Covalent bonds are, and we'll wrap this up pretty quick, and then I'll let you guys do your Lapster thingy. So covalent bonds are when we're sharing electrons. So like non-metals are going to share electrons. So when two atoms are kind of similar in terms of what we call electronegativity, they're going to share electrons. And covalent bonds or covalent compounds, they're not going to be very or they're not going to be able to conduct electricity. They're going to be very poor at conducting electricity electrically. So they're going to be pretty much neutral, but they can have, in some cases, have a weak partial charge, but not a strong electric charge like ionic compounds. So it's going to be much weaker than what you see with the ionic compounds. They're going to have lower melting temperatures and boiling temperatures. They're going to be liquids and gases, mostly at room temperature. And if they are solids, they're typically soft solids, right? Compared to what you saw with the hard, brittle of ionic compounds. Okay, so here we have hydrogen gas. So again, when we talk about whether things are going to happen, it all deals with energy, right? So the goal is to have the lowest amount of energy possible. So here, this basically shows you that the reason why the hydrogen gas is diatomic is because it's a much lower state than hydrogen being independent of each other, which is much higher in energy compared to it being a diatomic. So, and this just shows you that intermediate as it's kind of going on and on, right? So this guy is more energy, this guy is much less in energy when it's a diatomic. So this guy is going to be favored. Okay. So in the case of hydrogen interacting with hydrogen, this guy also is going to form what we call a nonpolar covalent bond. Okay. Now, the reason why it's considered nonpolar, you have two hydrogens. They're going to be equal. They're going to be pulling equally away from each other, those electrons. So they're going to have equal pull. They're like twins that are like playing tug of war with each other that are exactly the same strength and exactly the same height and everything. So there's never any movement towards one or the other. So they're sharing equally. So they're sharing these two electrons equally. Okay. Now, this again is called a nonpolar covalent bond. It's also called a pure covalent bond. So in your text, it's called a pure covalent. Okay, so these are examples of pure covalent bonds. H2Cl2. Okay, so again, they're sharing equally. How many of you guys have siblings? Well, I know there's 2 siblings in our class already.
I do.
Okay, which one is older? You or Michaela?
I am.
Are you the oldest of all your siblings?
Yeah, I'm the oldest.
Okay, so you may relate to this better than, and Michaela may relate to this better than others as well too. So
I'm
I
the
have 2
mentally older one.
What was that?
I said I'm the mentally older one.
Mentally older. Okay.
Angelina might contest that though.
I guess we get to test that in this class, right? So I have 2 sisters. Both of them are younger than me. So when I was growing up, we were kind of poor and everything like that. So my parents, what they would do, they'd buy us socks and underwear for Christmas for the most part, and then we would get one gift that we'd have to share. And like it'd be like we got an Atari one year, and man, that was a really big deal for us. And so the Atari, the way it worked out, or the way I thought about it was, I'm the oldest brother. I should get to play the Atari the majority of the time, and my sisters only get it a little bit of time. I'm saving them. I'm doing them a favor, right? So when my mom was at work, what I would do, I'd play the Atari and stuff like that, and then like 5 minutes or 10 minutes before she's supposed to get off, then I would give it to my sisters to play. And so when she walked in, they'd be playing the Atari, and then I'd go, well, it's my turn to play now. You guys have been playing it already. So then I go and play it again, right? When she's there. And so then that way I'm sharing the Atari, right? So, but is that sharing evenly or is that sharing uneven?
Unevenly.
Uneven, right?
Yes.
So when we talk about polar covalent, that's going to be that sharing unevenly. So there's 2 ways of sharing. We can either share evenly, where you get it half the time and I get it half the time, or we can share unevenly, where I get it the majority of the time and you only get it a little bit of the time. Okay. So pure covalent is when you're sharing evenly. Polar covalent is when you're sharing uneven. Okay. So examples of that is hydrogen chloride, and water, right? Let me erase this. Okay, so in the case of hydrogen chloride, chloride has what we call a higher electronegativity. And the electronegativity is an arbitrary number that has been defined. Well, a guy actually took the time to figure it out, but he assigned these numbers that don't have real value, but they kind of represent the energy that it is required to break bonds, okay? And I'll talk to you about that here in a second. And so chlorine has a higher energy than hydrogen. So because of that, it's going to want to pull the electron closer to itself. So chlorine is stronger than hydrogen. So the electron is going to spend more time around chlorine than it does spend around the hydrogen, okay? And so because of that, you're going to get what we call a polar situation where you form poles. One pole is going to be positive, partially positive. So it's not like the ionic charges where it's a complete charge. These are going to be weaker charges. So this one is going to be partially positive or a weak positive charge. And this one is going to be partially negative or a weak negative charge. Okay. And again, it's going to be, the electron is going to be spending more time towards the hydrogen. So we draw it as a pole, in a sense, with that arrow going in a direction that the electron is spending more time with. Okay, so this is the electronegativity. These are the values for your electronegativity. Again, these are arbitrary numbers that kind of represents the energy that is going to take to break those bonds, right? So in the case of chlorine, and this is hydrogen. Hydrogen is 2.1. So the way that we would calculate it, chlorine is 3. So we have hydrogen is 2.1. So we subtract the 2 from each other, and our value is 0.9. So anything that is less than or equal to 0.4 is going to be considered to be pure covalent or non-polar. Anything that is greater than 0.4 and less than 1.8 is considered to be polar covalent. And then anything greater than anything greater than greater or equal to 1.8 is considered to be ionic. Okay, so this is just basically showing you that. Questions, concerns, Cash? Okay, so we're going to stop right here. Okay, any questions? Any questions about the lab?
Are you gonna have the lab posted for Wednesday so we could have everything ready?
Yes, yes. I will have it posted before Wednesday, actually. Hopefully I'll finish it tonight or tomorrow morning. So at least by tomorrow afternoon, it'll be done.
Okay.
And again, you're gonna need these guys. If you're missing components, let me know. It should be you should have 2. You should have been able to, well, I can't even think straight right now. You should have 2 labs right now. One is going to be due on Wednesday, and one was due today, technically. Is that correct? Because you had the tutorial.
The simulation one.
Yeah, yeah. Both of them are simulations. Yeah.
Oops, simulation, sorry.
Questions, concerns, Cash?
Mauricio asked if there's a new lab today.
So there's not a new lab today, should be the simulation. And then the new lab is going to actually be posted later. Okay. There are no other questions. I'm going to let you guys go. And then I will see you guys.
Have a good night,
on
Dr. Henry.
Wednesday. You too.